Welcome back to this course on programming in Rust. Now, every function and every struct we've written so far has been tied to one specific type. So for example, a function that takes an i32, a struct that holds a string, etc., etc. And that's completely fine right up until you want to do the same thing for a different type. So say you want to write a function to find the biggest number in a list, and then later you want to find the biggest word in a list of words. You'd be writing the same logic for a totally different type. And right now, with the knowledge that we've covered so far in this course, you'd have to copy the whole thing out and write that logic for a second time. And that's what we're going to fix in this video. We're going to write our code once and have it work across different types. And here's the Rust part, without giving up any safety or speed. There are three features that make this happen: generics, traits, and lifetimes. And these three are very common in Rust. They're the backbone of pretty much the entire standard library. We'll work with all three of them when we build our next project later on, so it's really worth taking the time now to get comfortable with them. So here's the plan. First, we're going to cover generics. So we're going to write code that works with many different types. Then traits. We're going to use traits as a way of saying that a whole bunch of different types share the same behavior. And then lastly, we'll take a look at lifetimes. And this is how Rust makes sure that our references always point at data that's still around. We're going to tackle these in order because each one kind of builds on each other. So let's start with generics. So a generic is really just a placeholder for a type. Instead of tying a function or a struct to one exact type, like an i32, we leave a blank and let whoever calls it fill that blank in. Now, we don't leave it as blank in our code. We essentially write it as a capital T inside angle brackets, which just stands for type. So let me go ahead. I've created a new project called Generics, Traits, and Lifetimes. Again, this code will be available on my GitHub. And let's see a generic in action by typing the following. All right, let's open up a terminal. And we're just going to cd into that project and type cargo run. And there we go. I think I've, if I just open that up, yep, I put print instead of print line. That's okay. Happy little accident. Try that again. There we go, that's better. So let's take a look at what happened. So this largest function, just get out of the terminal for a bit, runs over our list of numbers that we've defined here. And then with no changes at all to the underlining function here, we've now been able to process that function over a list of words too. The only thing that it's really asking for is the type that can be compared, that you can ask is one value bigger than the other. And that's exactly what this partial OR after the colon is saying. Don't worry too much about this yet. It's trait bound, and we're going to get to those in a minute. And the pair up here, the pair struct, is a generic in the same way. So it will hold two numbers, two strings, whatever we hand it, it'll be able to hold it. In a lot of languages, this kind of flexibility does cost you a little something while the program is running. Rust is a little bit different, where it costs you nothing to do this, and that's down to something called monomorphization. I couldn't say it properly, but never mind. Don't let the word put you off or my bad pronunciation. Essentially, all it means is that when you compile, Rust will look at every actual type you used, and it will write out a separate specialized copy of the function for each one. So the numbers version and the words version quietly become their own dedicated functions. You essentially write one generic thing and you get the full speed of handwritten code for every type. So you get one definition and zero cost when it runs. Okay, now let's move on to traits. So a trait is a set of methods that a type can choose to implement. It's really our way of saying that all of these different types share this same behavior. And the best way to picture it is a promise. So if a type implements a trait, it's promising that it can do everything that the trait lays out. Let's see this in action. So I'm going to type out the following. All right, so let me go into my terminal again. And we'll run it. I've commented out a bunch of code, so we're going to get some just some warnings, but we've also seen that preview of the Art of the War is being printed out to the console. So essentially, here we're defining a trait called preview with one method, preview. And notice that it already has a body right here inside the trait, and that's a default. Any type that implements preview gets that behavior for free, unless it wants to do its own thing itself, and that's exactly what book here is doing. Here it's writing its own preview and overrides the default. So the default here is no preview, but for book, it's the preview of and then the title. Now, if you've used interfaces in other languages, this will feel fairly familiar to you. But traits can do a little bit more than interfaces, and we're going to take a look at that right now. We'll look at trait bounds. So this is where generics and traits meet. A bound is a simple idea. It says that the generic type has to implement a particular trait. And this is the missing piece from earlier. If T could be absolutely any type, the compiler has no idea what you're allowed to do with it, so it won't let you call anything. And essentially, the bound fixes that. It tells the compiler that this T definitely implements preview, so now you're allowed to call preview on it. So here we're going to take the same preview trait, put it on a brand new type, and then write a function that accepts anything that implements it. So let's write out the following. Okay, let me open up my terminal again. And I'm just going to clear that out. Let's run. Okay, so these two functions do exactly the same job. We're printing out the same output. So if I go back into the code, they're just written in two different ways. The first one uses the angle bracket form. See, look at that. T colon preview, which reads as T is some type that implements preview. The second uses a implicit preview shorthand, which reads a little bit more naturally for simple cases like this one. Either way, that bound is the thing that lets us call preview inside the function, because now the compiler knows for certain that whatever gets passed in has a preview method. And notice that podcast has a completely different type from the book that we defined earlier, even though they look like the same. But the same trait and the same functions work on both of them. And that's the whole point of shared behavior. The idea is that you write the function once and it works for every type that keeps the promise. Okay, and finally, we're going to take a look at lifetimes. Now, this is a feature that does trip up some people, so we're going to keep it really simple. Just to remind ourselves quickly, a reference is a borrow. Remember, that's a way to point at some data without actually owning it. Now, lifetimes are just labels that say how long the borrow is valid for, how long the thing that it points to is guaranteed to still be there. And that label is what lets the borrow checker make absolutely sure you never hold a reference to data that's already been cleaned up. Now, most of the time, Rust will work this out on its own, but every so often you kind of need to spell out that relationship for it. So let's go just above our main method here, and let's write the following. Okay, let me open up the terminal and cargo run. and it's printed out Ferris, but let's just take a look and see what this code is actually doing. So this tick A here, that little apostrophe A written just before the type is the name of the lifetime. You can call this almost anything. But what this signature is saying is the reference we hand back will live at least as long as both of the inputs do. We're not changing how long anything lives, not at all. We're just describing a relationship that's already present in the code, so the compiler can check it for us. So when you see these annotations, don't read them as you managing memory by hand. Read them as the compiler asking you to confirm something that it couldn't work out on its own. And that's really the secret to lifetimes. Okay, let's recap this lesson. Starting with generics. Now, generics let you write code once for many types. So instead of copying a function out for numbers and then again for words, you write it once with a placeholder, and Rust will fill in the real type. Traits are shared behavior. A trait is a promise that a type can do something, and different types can keep that promise in their own way. Now, what ties generics and traits together are trait bounds. And a bound says that a type must implement a trait, and that's what lets a generic function call its methods. And then finally, we took a look at lifetimes. And lifetimes say how long a reference is valid. They don't change anything. They just let the compiler check that a reference never points at data that's already gone. So that wraps up this video. In the next video, we're going to take a look at testing, which is baked into Cargo. And we're going to add some tests to the interpreter project that we built earlier. So if you like this video, give it a like. If you want to see that video or on testing and check out or any other videos that are part of this Rust course, please subscribe. Any questions, put them in the comment section below, and links to all the resources, including this code, will be in the video description. Thank you so much for joining, and I'll see you in the next one.